In the last section, we covered non-parametric models, built some decision trees, and performed some clustering. At this point, you're an expert in several supervised learning models. We're going to kick it up a notch and focus on some more advanced topics. In the final section of this course, we're going to split time between two fun topics, recommender systems and neural networks. We'll start with collaborative filtering, and then we'll talk about integrating content-based similarities into your collaborative filtering systems. Finally, we'll get into neural nets and transfer learning. Similar to past sections, we'll introduce the math and concept of each before getting our hands messy with some Python code. In this first video, we're going to introduce collaborative filtering and recommender systems. This video is going to start out a bit more conceptually, but I promise we'll get back to the nitty-gritty as quickly as possible. We'll start out by explaining what may constitute a recommender system, how users willingly share loads of data about themselves, or without knowing it, and then we'll introduce collaborative filtering. Recommender systems in general are near and dear to my heart, as I've spent the better part of the last 2 or 3 years researching and implementing them in my day-to-day, so I'm really excited to dedicate several videos to this topic. Whether you realize it or not, you interact with numerous recommender systems on a daily basis. If you've ever purchased from Amazon, or browsed on Facebook, or watched a show on Netflix, you've been served some form of personalized content. This is how e-commerce platforms maximize conversion rates and keep you coming back for more. One of the marks of a really good recommender system is that they know what you want, whether you already know it or not. A good one will make you really wonder, how did they know that? So it turns out that humans are extraordinarily predictable in their behavior, even without having to share information about themselves. And we call that voting with our feet, meaning that a user may profess to enjoy one genre of movie, say comedy, but disproportionately consume another, say romance. So the goal of a recommender system is simply to get you to bite, but the secondary goal generally differs based on the platform itself. So it could be to maximize revenue for the seller, satisfaction for the customer, or any number of other metrics. But what really makes these so interesting is that they're directly consumable by human beings, whereas so many other machine learning models exist to replace an automated process. Here's an example I like to use when explaining voting with your feet. This user says he likes football, hot wings, and water skiing. And yet his ratings history shows that he's thumbed up one wing restaurant, thumbed down another, and then thumbed up a movie cinema. So what this means is that there's something about the second wing restaurant that maybe he didn't like. Maybe it was the ambiance, maybe it was the wing sauce. Whatever it was, his interest in hot wings, his professed interest in hot wings, is more nuanced than he originally led us to believe. And likewise, he's expressed an interest in movies, even though he's not disclosed it. So the point is, people say more with their actions than they do with their words, and they're more honest with their actions than they are with their words. So we can exploit that with recommender systems to learn these nuanced patterns between items and people's interests. Collaborative filtering is a common family of recommender systems that we're going to spend a lot of time looking at. And it's based on a concept known as homophily, which is basically birds of a feather flock together. So that is, if you like something, people who also like that item probably share some other common interests with you. And now we have a good pool of interests to start recommending things to one another. In a typical collaborative filtering system, this is the format our data is going to resemble. Users along one axis, say rows, and items along the other, columns in this case. You might have explicit ratings, which are usually continuous along this continuum, or implicit, which are commonly binary. What we're showing here is explicit. The question we seek to answer is, what's the predicted rating for a user? But to get there, we have to somehow compute the similarities between the items. This is a form of collaborative filtering called item-to-item collaborative filtering, and we can only compute similarities between the items that have been mutually rated by a user. This usually works best for explicitly rated systems, and it's based on a paper that was published by Amazon several years ago. Computing similarities between items is fairly straightforward. We can compute pairwise similarities using one of several common metrics, including Pearson correlation or cosine similarity. For the sake of our example, we're going to use cosine similarity, and it's computed in a very similar fashion to what we looked at with clustering in the last video, Euclidean distance. However, this is computing similarity rather than spatial distance. So it's the exact inverse of the concept, but computed in a similar fashion. Since our data is so sparse, we're going to start out by putting it into a sparse CSR matrix using SciPy. And rather than having to store 32 elements, now we only have to store 14. And even this is a pretty dense matrix based on what we would actually see. So you can imagine how handy this becomes when we have tens of thousands of users and millions of items, if you think about like Amazon, for instance. Next, we're simply going to compute the pairwise cosine similarities of the transpose in the matrix. Super easy. There's something here we're going to come back to in a later video, but notice we have a lot of zeros in here. It's not that a lot of these are orthogonal, which mathematically is what a cosine similarity would represent with a zero. It's that we're experiencing something called the item cold start, where there are several items that have never been mutually rated together, and therefore we cannot effectively compute the similarity on the basis of ratings alone. Again, that's something we'll address in a bit, but leave it in the back of your minds for now. So for now, we want to know how to generate predictions for a given user, given their history and the computed item similarities, which we just computed. All right, in this example, we are basically using that same user, and we're just predicting for user 3. So computing predictions is easy enough in this algorithm. You just compute the dot product of that user's ratings vector and the similarities matrix, and then we're going to arg sort it descending. Very similar to how we did with nearest neighbors, but the inverse in terms of descending versus ascending. So things to note here: first predicted rating exceeds the scale of the ground truth rating. That's that 6.121. We only rated up to 5, but we can't guarantee bounded ratings. So we could either ceiling that or some other strategy. But the other thing is the second 2 ratings here actually ones that the user has rated before. And if you look back to the ratings matrix, both of these were rated as 1s by the user. So we can see that this is not a super great recommender model. Low rank, low number of users, and then again, it's toy data that I completely made up. So, roll with me here. And this also brings up a really interesting point I alluded to earlier. Recommender systems are technically supervised learning, and that we do have a ground truth, but they differ in the traditional sense of XY pairing, since our ground truth is technically our data itself. So in this case, we could look at the ratings for item 4 and 1 here and say how far were we off from the ground truth. And that's enough snippets. Let's look at the code for this algorithm in the package. This is item-to-item collaborative filtering. So over here in PyCharm, I'm going to drop down to the recommendation submodule and open up item-to-item as well as base. And then later we'll get into the examples. Let's start with base though. This base class is called Recommender Mixin. It's simply an interface that all recommender algorithms we'll cover in this course need to implement. And there's 2 methods. One is already written for all subclasses, and that's recommend for all users. And then the other is recommend for users. So we need to override this based on the subclass. First subclass we're going to look at is item-to-item collaborative filtering. Again, this is based on that Amazon paper. If you're interested in understanding the intricacies, just look up item-to-item collaborative filtering Amazon, and there's a paper that they published several years ago. Really good, easy, intuitive way to dive into the recommender system world. So all we're going to take here are 2 parameters. We have R and then we have K. R is our ratings matrix, different from other base estimators in that we don't have the corresponding Y. R is our ground truth as well as the training array. K is a parameter that we can use to limit the number of, the top number of items that are similar. And what it does is it helps reduce our space that we're comparing within and makes computations a little more easy. You don't really have to use this, but I'm going to choose to here. So our constructor, the fit procedure, is simply computing the similarity array via the compute sim function right here. What we're going to do, as we showed in the snippet, is we're going to take the R array, transpose it, so items are along the row axis, and then we compute the cosine similarity between rows, which are now the items. So we have an n by n for November matrix. N is the dimensionality of the number of items. And basically what we're going to do is we're going to say anything that's not in the top K, we're going to set to 0 similarity. And one of the strategies here is we could say anything that's not top K, we could later go back and impute with some content-based similarity, which we get into in a later video, or some other strategy, but it allows us to augment our similarity matrix in a way that otherwise we couldn't, and that's what we're doing. Arg sorting it descending, we want the most similar first, obviously, arg sorting along the columns. We take that similarity matrix, we store that here in self.similarity, and we're going to use that when we compute predictions down here. So recommend for a user, this is the function that we said we have to override in the super abstract interface, basically. And what we're going to do is we're going to take several arguments. So we have the user vector. It's just going to be an index in this case. And the number of recommendations we want to produce, and then whether or not we want to filter out ones that the user has already seen. So we get the user vector out of R. So going back to the example we had, let's say we pass in 3. We get index 3 out of R. And the recommendations, the raw recommendations, are going to be the inner product between the user vector and the similarity matrix, which produces a ND array, a 1D array in NumPy. We're going to get the item indices as just an A range in NumPy. And if we want to filter, what we're going to do is we're just basically going to pop out the indices that we've already seen, so we don't accidentally recommend those to the user again. And we're just going to order based on the descending arg sort of the recommendations. It's that simple. And then what we can do is we can limit them to the top n if we wanted to. Now, if you wanted to produce recommendations for everything, you could just pass none as n, and then that will give you everything. And we're going to return the items, the indices, and the recommendations, which are the predicted ratings for each of those corresponding items. So if we go over to our examples here, examples, recommendation, example item to item recommender, we're going to load up this interestingly titled dataset called Get Completely Fabricated Ratings Data. And I can load that up. That's actually down here in the recommendation submodule data.py. I've got to add a disclaimer. This is a completely made up data set of some of my favorite movies. And I, again, totally made this up. So I've got several users here. Let's pretend that user 0 is a classic 30-year-old millennial who loves, the nostalgia of the 90s. And so he highly rates The Princess Bride, Ghostbusters, Ghostbusters 2, everything that you would have watched as a kiddo in the 90s, late 80s. User 1 is a 40-year-old who really only likes action movies. And so maybe he rated Die Hard, or I don't have Die Hard in here. So we rated Pulp Fiction highly, right? User 2 is a 12-year-old whose parents are fairly strict. Okay, so we can assume that she's not watched Pulp Fiction or anything like that, but she has watched Ghostbusters, Ghostbuster 2, and the Goonies, and rated them all pretty highly. Good taste, okay? User 3 has seen it all pretty much and doesn't really care for the goofy stuff, but who rates the Goonies 2 out of 5? This guy and I wouldn't get along. And user 4 has just opened a Netflix account and hasn't had the chance to watch too much. So user 4 is probably going to be the one we're interested in producing recommendations for. This is all just going to be a NumPy array. I'm returning a dense array. You could return this as a sparse array, but this is the fake data set that we're going to use in all of our recommender system examples. And that's what we're loading up here. We're going to get the ratings matrix and the titles from Get Completely Fabricated Ratings Data. And we're going to create an item recommender with k equals 3, meaning we only retain for each of the items, the 3 most similar corresponding items. And then we're going to produce the recommendations for user 0 here. And recall that user 0 is the one who highly rated Ghostbusters, Ghostbusters 2, and the Goonies, as well as Jane Silent Bob. Great movie. Let's see what the top 3 rated movies are for user 0 if we go ahead and run this this recommender. All right, let's run this. User 0's top 3 rated movies are Ghostbusters, The Goonies, and Pulp Fiction. Well, it turns out user 0 had rated it highly, Ghostbusters and The Goonies. But 0, 1, 2, 3, 4, 5, 6 had not rated Pulp Fiction. So that could be a pretty useful recommendation. We also see that the mean average precision is roughly 2/3. Mean average precision is a metric that we're going to use for recommender systems. It actually comes out of information retrieval domain. It's not like, say, mean absolute error or mean squared error. What we're doing is we're saying, of the ones we recommend, what proportion of them existed in the ground truth set? In this case, which ones had the user rated highly to begin with? And this shows that the ones we produced were pretty good, right? The user had rated 2 of 3 of those pretty highly. So we can be confident that our recommender here is going to do pretty decently. All right, so in this video, you learned about item-to-item collaborative filtering.